Hello viewers, welcome to MathTech. I am MSc Sharma. Welcome to the lecture series of Abstract Algebra for CSIR NET, GATE, NBHM, TIFR, MSc Mathematics and IIT-JAM exam. This is lecture 6. So without a delay, let's start. Center of group. Let G be a group. The center of group G is denoted by ZG and is defined as ZG contain the element Z belongs to G such that XZ equal to ZX for all X belongs to G. Question number 1. Show that center of G is a subgroup of G. Center of G containing the element Z belongs to G such that XZ equal to ZX for all X belongs to G. Now E belongs to G such that X into E equal to E into X for all X belongs to G implies E belongs to center of G. Therefore, center of G is not equal to phi and it is a subset of G. Let A belongs to center of G implies AX equal to XA for all X belongs to G. Let B belongs to center of G implies Bx equal to Xb for all X belongs to G, which further implies Xb inverse equal to B inverse X for all X belongs to G. Now AB inverse into X, which can be further written as A into B inverse X, which can be further written as A into XB inverse, which can be written as AX B inverse, which can be further written as XA into B inverse, which is equal to X into AB inverse, implies AB inverse X equal to X AB inverse for all X belongs to G. Hence, by one step subgroup test, center of G is a subgroup of G. Question number 2. Show that center of G is an abelian subgroup of G. We know that center of G is a subgroup of G. For more detail, see question number 1. Let A belongs to center of G implies AX equal to XA for all X belongs to G. Let B belongs to center of G and center of G is a subset of G implies B belongs to G. Now A belongs to center of G and B belongs to G implies AB equal to BA for all A comma B belongs to center of G. Hence, center of G is an abelian subgroup of G. Next is, under what condition center of G is equal to G? Number 1, center of G equal to G if and only if G is an abelian group. Number 2, center of G equal to G if G is a cyclic group. Example number 1, center of Z or Z star equal to Z or Z star because Z or Z star is a cyclic group. Example number 2, center of Q, R and C equal to Q, R and C because Q, R and C is an abelian group. Example number 3, center of Q star, R star and C star equal to Q star, R star and C star because Q star, R star and C star is an abelian group. Example number 4, center of Z cross Q is equal to Z cross Q because Z cross Q is an abelian group. Next is group G B cyclic if center of G equal to G? Answer is no. For example, center of Z2 cross Z2 is Z2 cross Z2, but Z2 cross Z2 is not a cyclic group. Next is results. Number 1, if G has exactly one element of order 2, then the element of order 2 is the member of center of G. Number 2, if G has exactly one element of order 2, then the subgroup of order 2 is a subset of center of G. Next is center of K4. The center of K4 is K4 because K4 is an abelian group. Next is center of Q4. Question number 3. Find the center of Q4. Q4 containing the element plus minus 1, plus minus I, plus minus j, plus minus k, such that I square equal to j square equal to k square equal to minus 1. I into j equal to minus j into I, which is equal to k. J into k equal to minus k into j, which is equal to I. K into I equal to minus I into k, which is equal to j. Now 1 belongs to center of Q4, as 1 is the identity element of Q4. Minus 1 belongs to center of Q4, as minus 1 is the only element of order 2 in Q4. Since I into j is not equal to j into I, and j into k is not equal to k into j, implies I, j, k does not belongs to center of Q4. Also, I inverse is equal to minus I, j inverse equal to minus j, and k inverse equal to minus k also does not belongs to center of Q4, because center of Q4 is a subgroup of Q4. Hence, center of Q4 containing the element 1 and minus 1. Next is center of Un for each n. Center of Un is equal to Un for each n, because Un is an abelian group for every n. Next is center of Zn for each n. The center of Zn equal to Zn for each n, because Zn is a cyclic group for every n. Next is center of Dn for each n. For n equal to 1, center of D1 is equal to D1, because D1, which is isomorphic to Z2, is a cyclic group. For n equal to 2, the center of D2 is equal to D2, because D2, which is isomorphic to Z2 cross Z2, is an abelian group. For n equal to 3, D3 contains the element R0, R120, R240, L1, L2 and L3. R120 L1 is not equal to L1 R120. R120 L2 is not equal to L2 R120. R120 L3 is not equal to L3 R120, which implies R120 L1 L2 and L3 does not belongs to center of D3. Since R120 does not belongs to center of D3, which implies R120 inverse, which is equal to R240, also does not belongs to center of D3. Hence, center of D3 is R0, which is isomorphic to Z1. Next is results. Number 1, center of Dn for n greater than equal to 3 is equal to R0 if n is odd, R0 and R180 if n is an even number. Number 2, center of Dn n greater than equal to 3 is isomorphic to Z1 if n is odd, and isomorphic to Z2 if n is even. Example number 1, center of D5 equal to R0, which is isomorphic to Z1 as n equal to 5 is odd. Example number 2, center of D121 is equal to R0, which is isomorphic to Z1 as n is equal to 121 is odd. Example number 3, center of D20 is R0 R180, which is isomorphic to Z2 as n equal to 20 is even. Center of D1000 equal to R0 R180, which is isomorphic to Z2 as n equal to 1000 is even. Next is center of Sn for each n. For n equal to 1, center of S1 equal to S1, because S1 contain only the identity permutation or element. For n equal to 2, center of S2 equal to S2, because S2 is a cyclic group. For n equal to 3, S3 contain the element I, 1, 2, 1, 3, 2, 3, 1, 2, 3 and 1, 3, 2. We know that 1, 2, 1, 3 is not equal to 1, 3, 1, 2. Also 1, 2, 1, 2, 3 which is not equal to 1, 2, 3, 1, 2, and 1, 2, 2, 3 is not equal to 2, 3, 1, 2, which implies 1, 2, 1, 3, 2, 3 and 1, 2, 3 does not belongs to center of S3. Also 1, 2, 3 does not belongs to center of S3, which implies the inverse of 1, 2, 3 which is equal to 1, 3, 2 does not belongs to center of S3. Hence, center of S3 is equal to identity, which is isomorphic to Z1. Next is result. The center of Sn n greater than equal to 3 is equal to identity, which is isomorphic to Z1. For example, the center of S5 is identity, which is isomorphic to Z1 as n equal to 5 is greater than 3. Next is center of An for each n greater than 1. For n equal to 2, center of A2 equal to A2 because A2 contain only the identity permutation or element. For n equal to 3, center of A3 equal to A3 because A3 is a cyclic group. For n equal to 4, A4 contain the element I 1 2 3 4, 1 3 2 4, 1 4 2 3, 1 2 3, 1 3 2, 2 3 4, 2 4 3, 3 4 1, 3 1 4, 4 1 2 and 4 2 1. It is easily calculated that the center of A4 containing the identity element only, which is isomorphic to Z1. Next is result. The center of An n greater than equal to 4 is identity, which is isomorphic to Z1. For example, the center of A6 is identity, which is isomorphic to Z1 as n equal to 6 is greater than 4. Next is center of Glnf, where F is infinite field. The center of Glnf contain n cross n matrix whose diagonal element are A such that A is not equal to 0 belongs to F, implies the order of center of Glnf is infinity. Next is center of Glnf where F is finite field. The center of GLN-ZP containing n cross n element whose diagonal element are A such that A is not equal to 0 belongs to ZP, implies the order of center of GLN-ZP is P minus 1. Next is note. The center of GLN-ZP is isomorphic to ZP minus 1. Next is center of SLNF where F is Q or R, that is field of rational number and field of real number. Number 1, the center of SLNF containing the identity matrix if n is odd and containing the identity and minus identity matrix if n is even. Number 2, the center of SLNF is isomorphic to either Z1 if n is odd or isomorphic to Z2 if n is even. Next is center of SLNF where F is C, means field of complex number. The center of SLNC is isomorphic to Zn. For example, the center of SL5C isomorphic to Z5. Next is center of SLNF where F is finite field. Question number 4. Find the center of SL2Z3. The center of SL2Z3 containing a 2 cross 2 matrix whose diagonal elements are A such that A square equal to 1 mod 3, which implies the center of SL2Z3 containing the two matrices having element 1 0 0 1, 2 0 0 2, implies the order of center of SL2Z3 is 2. Next is result. The order of center of SL and ZP is equal to GCD of n comma p minus 1. Next is center of direct product of groups. The center of G1 cross G2 cross up to cross Gn is isomorphic to center of G1 cross center of G2 and so on cross center of Gn. For example, center of K4 cross S3 isomorphic to center of K4 cross center of S3, which is isomorphic to K4 cross identity. Question number 5. This question was asked in CSIR NET exam in June 2011. Let G be a group of order 77. Then the center of G is isomorphic to option number A, Z1, option B, Z7, option C, Z11, option D, Z77. The order of G is 77, which can be written as 7 into 11. and 7 does not divide 11 minus 1 implies G is isomorphic to Z77. Now the center of G is isomorphic to center of Z77, which is isomorphic to Z77, which implies the center of G is isomorphic to Z77. Hence option D is right. Question number 6. If order of G is 14, then find center of G. Order of G is 14, which can be written as 2 into 7, and 2 divides 7 minus 1, which implies G is either isomorphic to Z14 or isomorphic to D7. If G is isomorphic to Z14, then center of G is isomorphic to Z14. If G is isomorphic to D7, implies center of G is isomorphic to Z1. Next is centralizer of an element. Let G be a group and A belongs to G. Then centralizer of element A is denoted by C of A and is defined as C of A contain the element X belongs to G such that XA equal to AX. Question number 7. Show that C of A means centralizer of A is a subgroup of G where A belongs to G. C of A containing the element X belongs to G such that XA equal to AX. Now E belongs to G such that A into E equal to E into A implies E belongs to centralizer of A, implies centralizer of A is not equal to 5. Let X belongs to centralizer of A, then XA equal to AX. Let Y belongs to centralizer of A, then YA equal to AY implies AY inverse equal to Y inverse A. Now XY inverse into A, which can be further written as X into Y inverse A, which is further written as X into AY inverse, which is further written as XA into Y inverse, which can be written as AX into Y inverse, which is equal to A into XY inverse, which implies XY inverse into A equal to A into XY inverse. Hence, by one-step subgroup test, centralizer of A is a subgroup of G. Next is centralizer of A always an abelian subgroup of a group G? Answer is no. Under what condition centralizer of A is equal to G? Number 1. Centralizer of A equal to G if G is an abelian group. Number 2. Centralizer of A equal to G if G is cyclic group. Example number 1. 3 belongs to Z, then centralizer of 3 is Z because Z is a cyclic group. Example number 2. 1 belongs to Z star, then centralizer of 1 is equal to Z star because Z star is a cyclic group. Example number 3. Minus 1 belongs to Q, then centralizer of minus 1 equal to Q because Q is an abelian group. 0, 1 belongs to Z2 cross Z2, then centralizer of 0, 1 equal to Z2 cross Z2 because Z2 cross Z2 is an abelian group. Next, results. Number 1. If A belongs to G, then centralizer of A is contained in centralizer of A to the power n. Number 2. If A belongs to G, then centralizer of A equal to centralizer of A inverse. Centralizer of each element of K4. For all A belongs to K4, centralizer of A is K4 because K4 is an abelian group. Centralizer of each element of Q4. Question number 8. Find the centralizer of each element of Q4. Q4 contain the element plus minus 1 plus minus I plus minus j plus minus k such that I square equal to j square equal to k square equal to minus 1, I into j equal to minus j into I which is equal to k, j into k equal to minus k into j which is equal to I, k into I equal to minus I into k which is equal to j. Since 1 and minus 1 belongs to center of Q4, implies centralizer of 1 is Q4 and centralizer of minus 1 is Q4. I belongs to Q4, then centralizer of I is 1 minus 1 I minus I, because these elements commute with I. Minus 1 belongs to Q4, then centralizer of minus I is 1 minus 1 I minus I. Why it is so? Because the inverse of I is minus I. J belongs to Q4, then centralizer of J is 1 minus 1 J minus J, because these elements commute with J. Minus J belongs to Q4, then centralizer of minus J is 1 minus 1 J minus J. Why it is so? Because the inverse of J is minus J. K belongs to Q4, then centralizer of K is 1 minus 1 K minus K, because these elements commute with K. Minus K belongs to Q4, then centralizer of minus K is 1 minus 1 K minus K. Why it is so? Because the inverse of K is minus K. Next is intersection of centralizer of each element of group. The intersection A belongs to G, centralizer of A is center of G. For example, intersection A belongs to Q4, centralizer of A is 1 minus 1, which is equal to center of Q4. Centralizer of Un for each n. For all A belongs to Un, centralizer of A is Un for each n, because Un is an abelian group for every n. Centralizer of Zn for each n. For all A belongs to Zn, centralizer of A is Zn for each n, because Zn is a cyclic group for every n. Question number 9. Find centralizer of each element of S3. S3 contain the element I, 1, 2, 1, 3, 2, 3, 1, 2, 3 and 1, 3, 2. Since I belongs to center of S3, implies centralizer of I is S3. 1, 2 belong to S3, then centralizer of 1, 2 is I and 1, 2, because these elements commute with 1, 2. 1, 3 belongs to S3, then centralizer of 1, 3 is I and 1, 3, because these elements commute with 1, 3. 2, 3 belongs to S3, then centralizer of 2, 3 is I and 2, 3, because these elements commute with 2, 3. 1, 2, 3 belongs to S3, then centralizer of 1, 2, 3 is I, 1, 2, 3 and 1, 3, 2, because these elements commute with 1, 2, 3. 1, 3, 2 belongs to S3, then centralizer of 1, 3, 2 is I, 1, 2, 3 and 1, 3, 2. Why it is so? Because the inverse of 1, 2, 3 is 1, 3, 2. Question number 10. Find centralizer of each element of D3. D3 contain R0, R120, R240, L1, L2 and L3. Since R0 belongs to center of D3, which implies centralizer of R0 is D3. R120 belongs to D3, then centralizer of R120 equal to centralizer of R120 inverse, which is equal to centralizer of R240, which is equal to R0, R120, R240, because these elements commute with R120. L1 belongs to D3, then centralizer of L1 is R0 L1, because these elements commute with L1. L2 belongs to D3, then centralizer of L2 is equal to R0 L2, because these elements commute with L2. L3 belongs to D3, then centralizer of L3 is R0 L3, because these elements commute with L3. Some important results. Number 1, if A belongs to center of G, then centralizer of A equal to centralizer of A to the power n. Number 2, if H is a unique subgroup of order 2 of a group G and A belongs to H, then centralizer of A equal to centralizer of A to the power n. Thank you very much for watching my video. If you like the content, please do like, share and subscribe my channel. If you have any query, comment me. Thank you very much.